So I'm done talking about how to do stuff as far as the binary exploits go, as far as Razor goes. The last level, which is 14, there's no source code. So that's the one where you have to actually reverse engineer, which you're probably familiar with from 2400 or other classes. Everything else, you had source code, doesn't necessarily make it easy. Today I'm going to talk about some countermeasures, which is not what this class is primarily about. We're not normally about defending against attacks, although it's a very useful skill, obviously. But I'll talk about some stuff briefly in that respect, and also payloads. So let's go ahead and get started. There are a lot of other local attacks, and by local I mean you're already on the machine and you're trying to escalate, take advantage of set UID, set JID binaries and things like that. There's this, if you really like what we've been doing, if you just think this is the greatest thing you've ever done with your weekend, then there is another set of binary level attacks that I've done called Vortex. Has anybody ever done these? They're on overthewire.org. They're way harder than Razor. So if Razor's not hard enough and you're not feeling challenged, go to Over the Wire, and Over the Wire has a bunch of different games. The easiest one I think is called Bandit. And Bandit is just like, you know, can you type your name or something? It's really quite simple. It's mostly like helping you to learn shell, like bash. So you still are leveling up, but the challenges are fairly straightforward. And I think there are 5 or 6 of them, and of the ones I've done, Vortex is the hardest. And Vortex is very much like Razor. And to get started on this Vortex machine, you have to first read, I think, 4 numbers from a port and then add them up and then send the sum back. Does that sound familiar? You did that already, right? And you got a password. That password is to start this Vortex war game. So you've already done the first step. So if you want to, you can go and do it. They do a lot of buffer overflows like we've been doing, but also there's level 11. I think there are like 35 levels, and I've been to 27, and they just get insanely hard. You know, and that 27 probably, I did it over 6 months, and some of the levels took me much longer than anything on Razor would have taken me if I had approached that as a student. But there's a heap overflow. What's the heap?
Memory.
Yeah, so malloc, right? You don't have this in C++, right? You use like new, create objects. But in C, there's a kernel call called sbreak, which sets the amount of dynamic memory that you ask the operating system for. But then if you want to micromanage that chunk of memory, there's a C runtime library. There's a libc set of routines that have, for example, alloc and malloc and calloc. And then how do you free that stuff? With free, right? But those are not actually calling the operating system. Those are just the C runtime allocating blocks of memory, keeping administrative metadata to keep track of where that chunk that, you know, if you say I want 500 bytes, it's going to allocate 500 bytes. It has to keep some bookkeeping to know this is 500 bytes that I've allocated to this program. And then when you free, it's going to free that 500 bytes and return it back to a pool. If 2 free blocks are adjacent, it should merge them, which is often called a coalesce. It used to be in some data structures class they would have you implement this stuff. Did anybody ever implement this stuff as part of OS, or you did?
In OS.
In OS, okay. I mean, it's not incredibly relevant to OS, but it keeps you busy, I guess. If there's a bug in that code, then there are possible overflows and like a double free. Let's say you free a piece of memory and then you free it again. It could invoke depending on which heap implementation you have, could cause a vulnerability, security problem. So on Vortex level 11, there's such a thing. It's a heap overflow, not a double free. But double frees can also lead to exploits. So you'll see these from time to time crop up. Extremely intimate details about how the heap is implemented are involved in order to take advantage of this stuff. All right. So language-specific hacks, detours stands for destructors, which is after a program runs, you exit main, right? You return from main. The program doesn't necessarily end. It returns back to the init code that called main in the first place. Sometimes it'll call some cleanup code. It'll close open your open file descriptors, detours, destructors, so it's supposed to destroy objects. Sometimes there are vulnerabilities related to that stuff. And then kernel hacks, so if there's a bug in the kernel, there's an entire book about kernel exploitation you could go read. We didn't touch that at all.
Rootkits.
Obviously. Sorry?
Rootkits.
Rootkits. We're going to do that today. Yeah. All right, so let's talk about countermeasure. This is blue team stuff. This is defending against these kinds of exploits. Obviously, the best thing to do is just not have bugs, but that's not possible. So revisiting the levels that we've seen, level one, the problem there was that what? The hash was exposed, right? Remember, I accidentally put the hash of a password into etc group instead of etc gshadow, and you were able to use John the Ripper or something to break it. So exposing hash of passwords is dangerous because we can brute force passwords. Don't pick dumb passwords. So it was an easy password. What was the password? Security or something?
Yeah.
Security. There was this guy, Aaron Barr, who was an MBA, so he's a business person, and he decided to infiltrate the group called Anonymous. Have you heard of Anonymous? These are a group of so-called hacktivists, people who are hacking for a purpose that's related usually to politics or public policy. And Aaron Barr was this business person who decided to infiltrate Anonymous, ingratiate himself, pretend he's one of them, in order to expose them and so-called dox them, right? What's doxing?
Like your public.
Yeah, publish your name, your address, your social security number, or your email, all that stuff publicly and say, you're this person in Anonymous. He wanted to out all of these people, dox them, expose them, in a way of promoting his own cybersecurity company. So he had a company that he had started. And so he did ingratiate himself in the group for 6 months or something, posing as somebody else. And then he announced on Twitter that he had found out who these people were. He was going to expose them at this upcoming conference. He had this big talk promoting his company. And Anonymous found out about this, and they broke into his website. And it was like, you can go read the article. It's the most embarrassing list of like basic security vulnerabilities any website could ever have. Like he had a dumb password, and it was unsalted MD5. What does that mean, unsalted MD5?
It's encrypted using MD5, but he didn't have like random characters appended to the front.
That's right. So that means you could focus on all of the passwords at once, not individually. Yeah, and there was an SQL injection, and his defense was, well, we just hired some web shop to do our website. We didn't do that ourselves, but still, you're a security company. And anyway, it's a really entertaining article.
Sort of a question maybe about the last slide, which is sort of just about this like don't have bugs. Which
Yeah.
I guess I've been thinking a lot about the whole class. Like a lot of the exploits are sort of like C vulnerabilities, things like built into the language.
Yeah.
Like what are your thoughts on it? I guess I've never really used it, but like I feel like there are these languages like Rust or sort of like, I don't know, people saying like, well, C is just sort of like an antiquated language. Sort of, we have a lot more experience now with security and like how to design a safe language. Like, what about just not using C? Like, is that
Okay.
like a better choice than something?
So we could not use, so C has a lot of risky features, right? Like string copying instead of ester. But there are literally billions of lines of C out there that we still need to use. I mean, we could rewrite it all, but we don't have the human power to do so. Plus, C is still the best choice in a lot of cases. I mean, you can't write an operating system in Java. Actually, I say that, and then I think there is an operating system written in Java. But Java has a JVM, and if you try to overwrite an array, babysitter catches it and raises an array out of bounds exception. And it does garbage collection. So there are no pointers, right? So all kinds of really safe environment stuff. But you've got this overlord called the JVM, the virtual machine, that is running your code for you, interpreting your bytecode for you. And that's slow. And it's not amenable to writing like device drivers for a video card or in a lot of embedded systems. And I've done some consulting where I wrote code for one of these smart thermostats. Like, what's the most popular one called? Nest, right? But there are also a bunch. Nest is like $200 or $300. There's like $30, $40 ones that are just basically from China, and they have most of the same features. I wrote the crypto for one of them, one of the local ones. Everything's in C. The entire operating system's in C. So I'm not sure C is ever going away in our lifetime. We could, go to a similarly efficient language that's still going to compile all the way down to machine code with no oversight, because the oversight slows you down, but just don't have string copy. But I think you just get this culture of tradition where you've got, the older generation still writing in C, and so the newer generation has to modify, maintain, update, extend that code. Therefore, it gets into this mode where everything's in C, and then when they make new code, they just keep doing the same thing. You see some departure from that. You'll see now writing in Go and stuff like that. But there's still a lot of C out there.
Yeah, I guess it's not so much like, obviously you have to deal with existing code, but like I think some companies, are like, we do have an option, like should we like wipe the slate clean or something and use Rust or Go or something from, just because the safety issues are so big.
Yeah.
Obviously.
If you want to write the fastest possible code, then you're going to need a language that doesn't protect you from yourself. It gives you all the power of assembly language. But it doesn't have to be as bad as C, because C has this library of bad stuff. You don't need the library of bad stuff. But you do need like pointers and things like that that are already inherently dangerous. And as we're going to see, a lot of these binary exploits, like for buffer overruns with canaries, which we're going to talk about today, and ASLR, which we're going to talk about today, these countermeasures do make it way harder to exploit this stuff. So it has been effective to some level. And now most of the exploits you see today are going to be either bespoke, in other words, they're custom exploits against some bad piece of software, or they're SQL injections, or CSRF, or cross-site scripting, or other kinds of web-based. Like the next set of exploits we do are more common and relevant for today's levels of attacks than the stuff we just did. 10 years ago, 20 years ago, this was more relevant. Okay.
Is it fair to say that between like ASLR and canaries and now 64-bit, like these kind of exploits that we've been doing are kind of like there's not even really much of a point of attempting them if somebody has all three of those things? No, they happen
all the time still.
They still happen all the time?
Yeah, not to the level that they used to in the 90s. In the 90s, every 10 minutes you would hear about some binary exploit. Now you hear about a couple per year that are important. But people have figured out how to get around ASLR and canaries and things like this. Sometimes doesn't seem to be any way to do it, get around it. Like it seems like the countermeasures completely stop the fact that there is a buffer overflow here, but it's not exploitable. But in other cases, people are clever enough and they figure out a way to exploit it, usually in combination with some other kind of vulnerability, that each one on its own wouldn't be exploitable, but the combination is. Okay. Levels 2 and 3 don't use things that depend on the environment, like the path variable or the home variable or things like that. Levels 4 and 5, sanitization maybe would have helped. It's hard to sanitize properly. People usually screw it up. Do you allow slash in a file name? Do you allow dot in a file name? Then you maybe will allow dot dot slash. That was one of the exploits, was to use the dot dot attack, right? So you want to allow a slash and you want to allow a dot, but certain combinations you want to disallow. That can be very hard to do. And as we'll see when we do SQL injections, sanitizing inputs is not even the right way to to defend anymore using parameterized queries is, and we'll talk about that. All right, buffer overflows, don't have them, of course, is the best defense. There's static analysis tools that are out there. What does that mean, static analysis?
It just has like a set like list of things that it tries.
Before your code is compiled, you start running analysis on it to check whether.
Okay, so it means that at compile time, don't run the code. The compiler, or the tool that's like a compiler, looks at your source code and goes, there's a buffer overflow here, right? Now that's not always possible, because sometimes the overflow doesn't occur until runtime, and that it occurs because of a bunch of pointer math that's happening at runtime that you can't foresee at compile time. In fact, this problem is NP complete to do it completely at compile time. But it does, what it does is it'll say, this variable can range anywhere from 1 to 17. And this one can go anywhere from 2 to 9. And therefore, the sum of them can go anywhere from 3 to 26. So it tracks the range of possible values for every variable to see if it ever could add up to something that would overflow the end of a buffer. And then it keeps track of anything that is tainted by user input. So as soon as something can be touched by user input, that variable is considered untrusted. And that distrust is tracked through the compilation process. And it tries to flag like there's a potential problem here, here, here. That's called static analysis. Used to not be very useful about 20 years ago, but it's gotten really advanced now. A lot of the PL people work on this stuff. Java, you can't have a buffer overflow in Java, right? And there are no pointers. And it's gotten a lot faster now. And a lot of it's JITted, right? What's JIT?
Just-in-time compilation.
Just-in-time compiled. So pieces of code get compiled into machine language just in time, and then if they're looping or run repeatedly, it's cached. So you have machine language run instead. ASCII armor. This is the first countermeasure that was suggested for buffer overflows. So if your text, if the only executable range is in this range of addresses, then how come shellcode gets hard? So all your text, all your machine language has to be in the range from here to here. And this is the only segment of memory that's marked executable, nothing higher. Why is that a problem for the exploiter or the attacker?
You can't execute on the stack.
It's hard to put code there.
You'd have to put code here.
You can't use stack addresses. Usually higher memory, you lose out on what kind of memory you can access.
Okay, so if this is the only executable place, you have to inject your shellcode here, and then you have to jump to it, which means you have to inject an address in this range, which is going to have a 0 byte. So a lot of our exploits, we can't inject zeros, right? Because that's going to terminate a string copy. It's not a great solution, but it's called ASCII armor. Make the stack non-executable. OpenBSD calls it W XOR X. Exec shield is what the Red Hat calls it. DEP, which is data execution prevention. Get it? Data execution prevention. Don't let people execute data, because that's what we've been doing. PAX, that's what Ubuntu has. PAX includes many countermeasures, not only non-executable stacks, but also canaries, which we'll look at in a second. So you can't, therefore, inject code into the stack and jump to it, like we've been doing all semester. You can't run stuff in the buffer or in the NP array. You can still inject parameters and do return to libc, return-oriented programming. In 2400, I think you do one exercise of return-oriented programming. Canaries. So a canary, which I've alluded to before, and you may know what it is, but what happens is at runtime, the runtime system, before it calls main, generates a random 4-byte quantity. This is on a 32-bit machine. And that's called the canary. It's called and every time you run the program, you get a different one, or you get a newly generated canary. And then it pushes it between the save frame pointer and the locals. So your stack's going to look like this. I is a local, temp is a local. Then there's a canary. So the way this gets laid out is, the usual parameters are on the stack. The call to the function pushes the return address on the stack. The preamble saves the frame pointer, and then writes the canary onto the stack, and then allocates the locals above that. Okay. When the function leaves, when it completes, it cleans up its locals and checks to make sure the canary is still intact. If this has been changed in any way, it says stack smashing detected, program aborting, and it stops. You've ever seen that error in your life? Stack smashing detected. That means somehow your stack got corrupted and this canary was killed. And so the runtime decided to abort in that case. Okay. Why is it called a canary?
Coal mine?
From coal miners, right? Coal miners used to actually take a living bird into the coal mine, and if it died, everyone has to GTFO, right? Because it means there's like noxious fumes leaking from the mine shaft, and people are going to get killed. So that's an early indicator. If the canary dies, abort, and that's what it's used for here. Why random?
So you can't examine it, the debug.
So after every
Right.
execution, it has to change.
Say again?
After every invocation, it has to change, because if you keep it to the same value after every invocation, you can just leak it out using printf or some format string or that, and you read it.
And if you know it, if you, the attacker, know the value of the canary,
You can control canary.
what?
You can control canary.
How?
Overflowing the canary's address.
Exactly. Okay, so the point of this thing is, right, if you want to exploit a buffer overflow, let's say that there's a buffer here that has an overflow vulnerability, just like in the homework. What do? You overwrite the buffer down deeply enough to hit the return address, and then you take over this program. Okay. In order to do that, you're going to clobber the canary on the way down as you overflow, right? So this is detecting anything that overflows a local and goes past the canary into the sensitive region of the stack that has the return address. If you knew the value of a canary was 1, 2, 3, 4, then what you would do is you'd overflow the buffer, and then when you got to the canary, you would just inject 1, 2, 3, 4 to leave it untouched, right? Overwrite it with what it's supposed to be, and then continue on down to the return address and take over the program. So the canary needs to be unpredictable, because otherwise the attacker just overwrites it with the same thing. If there's a 0 in the canary, then I guess you can't, right?
Is the canary checked after every step, or
Only on exit of the function.
Okay.
Yeah, if we check out every single operation, it would be horrendously costly, right? It's already bad. Like you'll see, remember -F no stack protector? That's how we compile the homework. That no stack protector means don't use canaries. You'll see super high performance code compiled that way because they don't want to pay the price to insert the canary and check the canary on every function. So it's like aggressively optimized code will take that option out. And they'll be like, we're not in a security context, so I don't care. But yeah, every function has to place it and then check it on the way out. All right. Substantial overhead. If you can write to arbitrary memory, not an overflow, but you just have the power to write anything, anywhere, canaries don't help. Like format string vulnerabilities, right? We just surgically choose an address and a value and we put it there. We don't overflow any buffers. So this is not a defense against format string attacks. Canaries are always in writable memory, of course, because the runtime has to write. There have been vulnerabilities that have allowed people to bypass canaries. Here's an example of something that might happen. So suppose there's a buffer with an overflow problem, like this user input buffer. It's 256 bytes. And you can overflow into a pointer that lives below it. Then you could overflow, and then later in the code it does this, copies from here to here. You could overflow, set this pointer to the return address, and then on the copy, write directly to the return address going around the canary, something like that. Sometimes a weak source of entropy is used to generate the random numbers. If you can predict the canary, if you have any idea of roughly what it'll be, maybe you have a 1 in 256 chance of hitting it, you can just try and guess. And then on average, about 256 tries will be required. You'll hit the canary value and you'll win. Once again, if you can guess the canary, you can just override it with the same thing, and then it won't blow up on function exit. For the child attack, there's a this is a clever attack. I haven't implemented it, and I sometimes have assigned it as extra credit, but I'll just show it to you with my eraser. Thanks. I'm gonna try the rag first. All right, so this has happened. So this is a server that uses canaries. And it's a server that serves a web service or a network service. And what it does is every time a connection is made, it forks itself and hands the connection to a child. Does that sound ridiculous? That's a common thing, actually. You're a server, you listen on port 80 or port whatever, and a connection comes in, you accept, that's the call, the connection, and then you fork process, and that forked child is dedicated to just serving whatever customer is connected. And then you go back to listening in the parent. You don't wait. And that way, if somebody else comes in, you fork yourself again and make another child, and that goes to that connection. And then when the child dies, the connection's closed and it returns to the parent. Okay. So here's the server. It has a canary value. When it starts up, the canary is randomly generated. And what happens when the child is forked? Is it the same canary or does it generate a new one? It's the same, because remember, a fork is just a clone. So it has the same canary. All right. There's a buffer overflow vulnerability. So the problem, of course, is that there's a buffer overflow vulnerability that's here, but also here, because they're the same process. But there's a canary. So if you start to overflow the buffer too far, you're going to touch the canary. Almost certainly you're going to perturb it to some other value, and that's going to kill the process. But the nice thing about this setup is that if you overflow the buffer here, then when the canary blows up, it only kills the child, but the parent stays alive with the same canary value. So what could we do? You have this sort of like oracle. You have this query thing you can query, which is you can blow up the child by setting the canary to the wrong value, but then you get another shot because you can spawn a new child with the same value and try again, and that target's not moving. Right? You're trying to get this canary value. So what could you do? I mean, you could overwrite, let's say this is 32 bits. You could overwrite the canary with 0, 0, 0, 0. I don't know if you can do that one because it's zeros. But you could just try all of them, right? 1111, 1112, 1113, just keep incrementing. The child dies, go back, spawn a new child, try the next. Then you've got 2 to the 32. It's 4 billion attempts. Someone might notice. That's a lot of children to spawn. There's a smarter way.
You just like find the right byte for each byte in the 32 bits.
How do you do that?
Just modify that byte. It should only take about 8 attempts on average to find the right one. So,
Explain. So I've got this child, it's got a buffer overflow vulnerability.
so you can override it. And couldn't you just overwrite it until not the full 32 bits, but just like the 1 byte of it?
1 byte, okay. So let's overflow the buffer plus 1 byte of the canary, just the first byte. Plus first byte of canary. And then what's going to happen if you don't get the right first byte, it'll die. So eventually you'll overwrite the first byte and it doesn't die. That means you've got the right first byte of the canary, right? How many times does it take to find it? 256 is the worst case. 128 is the average case. 50-50 chance it'll be first half or second half. So 128 expected queries to get the first byte. And by say get, I mean you overflow and the child doesn't die. That means you've got the first byte. Then what?
Do that 3 more times.
Okay, now you overflow the buffer plus the first byte using what value? The one you discovered. And then you try all possible second bytes. So you only overflow the canary up to 2 bytes of it, keeping the first byte fixed at whatever the one you discovered was, and then you do the second one.
It's like lock picking.
Sorry?
It's like lock picking.
It is like lock picking, yeah. So, and you got 4 bytes to do. So we have an expected how many tries to get the entire canary?
512.
512 tries. And then you have the full canary value, and now you can just overwrite the canary. And now you can go into the server maybe and overwrite the canary, and then overwrite the return address, take over the server. A lot better than 4 billion tries. Okay. I have an implementation of this if you want me to post it. Play with it. Nothing else to do. ASLR. Remember ASLR? That's when the stack is moving around. Would that have made the homework harder? Infinitely harder, right? Every try, it's moving around, and you have to hit your shellcode, which is also moving around. All right, so mmap, the memory map call, will map these segments, text, data, and stack into random virtual addresses. But the randomness is constrained. It's not just any address. So it's not going to put the stack at like 1, 2, 3, 4, 5. It is going to align it on a page boundary for efficiency reasons. So here's PAX. PAX was the Linux version. It has canaries and ASLR. And non-executable stack. That's all packaged together to call PAX. Text and data is randomized with a 16-bit base and stacked with a 24-bit base on a 32-bit machine. So your text and data is going to look like this. These are fixed. This is always 0. And the random stuff are these X's. And these X's are bits. So how many X's are there? How many bits of randomness?
16.
Looks like 16 bits of randomness. So 2 to the 16 different values, which is what? 65,536, right? 65,000-ish different possible values. If you're throwing a dart at 65,536 points, what's the chance of success? 1 in that number. So you have a 1 in 65,000 chance of just guessing it. That doesn't sound great, but it's expected 30. Is that even right? It's not right. No, the expectation is 65,536. I don't know where I did the math wrong. Anyway, there's a paper called PAX ASLR where a Stanford team takes an Apache server, puts in a simple buffer overflow, and takes advantage of the fact that forked children's will crash and respawn, and just tries 65,000 stabs in the dark and eventually hits it. Takes about 216 seconds to win, on average. That's not that bad. So if you have a victim that is resilient enough that you can keep guessing, it'll keep coming back to life and giving you more tries, 65,000 tries isn't that bad. So ASLR is not that effective on 32-bit machines. 64-bit machines, forget about it. There's way more randomness, and you get into like billions and billions of different possible positions for the stack. So on a 64-bit machine with a non-executable stack and ASLR and canaries, it's very hard to exploit buffer overflows, and it still has happened in the face of this. All right, so as a result, now we're seeing more web-based attacks, not as many binary level attacks, right?
Is there some kind of defensive mechanism where if the child, if there was a step with the child returned that it was stack smashed, that the server will just not, fork another child?
Yeah. You could definitely look at that sort of thing. Yeah, you almost never see it though. Format strings, that's the last thing we did. Disable %n. %n was the really useful thing that, right? It seems silly, like I'd never heard of %n before these attacks. Who uses this? But you break the standard implementation if you take it out. Microsoft already doesn't support %n in its C compiler, just for this specific reason. ASLR helps, because even if you can write anything you want anywhere you want, where should you write it? Because things are moving around constantly. In the year 2000, there were thousands of these vulnerabilities. Largely, the countermeasures have gotten rid of them. In particular, static analysis is useful to find form. So it's easy to, for a compiler to look at your code and go, you've got a printf right there, and it doesn't have a format string. Or it's got a variable that's tainted by user input. That's easy to figure out. Unlike buffer overflows, which are incredibly hard to find. They can come as a result of thousands of mathematical operations on pointers that result in a buffer overflow. These are easy to find. So people just ran compiler with warnings turned on, found all of them, fixed them, and now they're gone. So you don't see these as much, nearly as much. All right, so those countermeasures, that's how to defend against this stuff. Defending against the next set of stuff we do, the web-based, is way harder and way more relevant. All right, so on a side topic, what should you do if you break in? This is, on the homework, you just go on to the next level and you write it down, you hand it in, you get points in the class. But if you were really a pen tester or really a malicious person and you broke in, you got to root on a machine, what would you do? I mean, let's say you open a reverse shell. Remember reverse shells? Now you're on the machine. That's not persistent though, is it? Like as soon as the machine's rebooted, you have to do it again. Maybe they'll patch the way you got in. Now you're locked out of the machine. You could add a new user. That might get spotted by an admin. Who's this new user? Let's remove it. So rootkits are the answer. What's a rootkit?
So we did try to mess around with rootkits in the other class, and rootkits are basically which give you root access every single time by using kernel exploits.
Okay, so it comes from this idea that you have access to root, but the features of a good rootkit are persistent access, so if the machine reboots, your access doesn't go away. And the huge one, don't be noticed. And that's hard. So you want power, which means be root. You want resiliency in case the machine's rebooted. And you want to be invisible. Power is easy. Resilience means you put it into the boot sequence. But invisibility is the challenge. So if I do a PS or top or something, I should not see any process related to your rootkit. Your rootkit should hide itself. If I look on the disk, I shouldn't see any files related to your rootkit. If I look at my logs, I shouldn't see any logs activity. So your rootkit's going to hide itself so perfectly that it doesn't leave any traces. So let me go show you one. This is extremely basic, and I just want to capture the idea of how something like this might work. The only right way to get root and hold it is to embed malicious code into the kernel itself. Now, who's ever modified a Linux kernel? A couple of you have, right? By modifying the Linux kernel, you have to go to the Linux source code. It's written in C, but it's this weird kind of C. Like you don't have printf, but you have printk, this kernel version of printf. And a lot of there's not just like a normal system call. You don't just go int 80 because you're already in the kernel. And there are all these certain calling conventions. So coding in the kernel is very weird. And if you code in the kernel, then you have to recompile the entire kernel and then update your operating system. So an easier way to modify the kernel in Linux is to use what are called LKMs, or loadable kernel modules. This is from the old ancient times now. This used to be newfangled, but now it's been around for a long time. You can basically write a module that will be loaded into the Linux kernel and be running alongside the core kernel code. But you don't have to recompile the kernel. You can write it as a separate module in user space and then just load it, install it into your operating system, and it just runs, which is extremely powerful and yet extremely dangerous. So that's the way we're going to build a rootkit right now as a kernel module. And that makes it really easy, at least easy to install. So rather than do it live, I already have one prepared. And I stole this from somewhere, at least the core of it, and rewrote it. It was originally called Suck It and was in Frac. Anybody ever heard of Frac? What's Frac?
I think it's a website which publishes.
It's like an online magazine.
Yeah.
The other big one is 2600, if you've heard of that. 2600 is the frequency that telephone signals are sent over for administrative data. In the old days when phone phreakers used to mess with the phone. This is back when you actually hang up a phone by hanging up something. Okay, so that's the original name for this thing, Suck It. I gotta be on Razor, I think. Oh, not again. Am I on that stupid guest?
It's probably, you have to go in your Wi-Fi settings. It's set at a higher priority than your.
Yeah, or
than
just
the
forget
actual-
the guest one because I
Yeah.
never actually want to be on it. Why? Oh, because I rebooted this morning. Okay. All right, so here's my rootkit. It's not actually that long. It's 134 lines, but it's also not great. Like, it doesn't hide itself very well. And the original version of the rootkit, I'll explain, it used to do better stuff. Okay, so some of this stuff is going to look kind of weird because it's coding for the kernel. There we go. So there's something called the system call table in the kernel. And what it is remember when you do an int 80, what's in the EAX? You do an int 80.
B. The byte B.
The byte B for exec VE, or the number 1 for exit, or it's whatever the service code is. So when you're telling the kernel, I would like some service from you, you tell it which service in the EAX, and then all the parameters were in EBX, ECX, EDX, all that, right? We didn't push parameters on stack. We put them in the registers. When the kernel first wakes up, because you're calling it with an int 80, it looks at the EAX and indexes into a table of pointers. So if you've got a 1, then the first slot in the table is going to be a jump to the exit code that implement exit. If it's a B or 11 in the EX, it'll go to the 11th slot in the table, which will be an address to the code for exec VE. So it's just a jump table. Same way that like switch statements are compiled into jump tables. So this jump table, what I'm going to do is in this code, I'm going to go take this jump table and modify it. And you're like, wait, you can't modify that table. That table's critical. It is critical, but I'm writing kernel code. I can do whatever I want. So I decided to do 2 things in my rootkit just as a demonstration. So this is my jump table. What's it actually called? Syscall table. Let's call it that. It's just a table of addresses. So the 1 is going to have an address that goes to the code for what?
Let's see.
Down here, 11, that's going to go to exec VE. And this goes on for a few hundred entries, a whole bunch of different calls. So what I'm going to do, just for fun, is I'm going to take over 2 system calls. The one for write, and the one for set REUID. I don't know if the numbers are here or not. I don't know them offhand. We could go look it up. Maybe I will, just to. Anybody see it? It's really small. 4. And then, what else was it? Set REUID? $70. Okay. When would you ever use write? W-R-I-T-E as a system call? When would a program, a C program, any program, use that system call? When you do a read and a write from C, you're actually going through a layer. You're going through the C runtime, but it ultimately will go down to read and write. I think a read's at 3, isn't it? Yeah. It'll eventually devolve to this 3 and 4, this system call for read and write. Printf is not a kernel call. Printf, it goes to a library, the C runtime library. But eventually it'll become a write to what file descriptor?
1.
1, standard out, right? So it's going to actually do a write. Network traffic. When you write to a socket, remember everything in Linux is a file. Your terminal's a file, your network socket's a file, your printer's a file, and of course a spinning disk file is a file. So when do you do a write? Almost always. That's the only way to actually interact with the device, to read from it and write to it, or to go through these system calls. So everything goes through this call. I'm going to hijack this thing. And by hijacking it, I mean normally this entry points to a blessed, untouched, perfectly written piece of code that the kernel authors carefully wrote. And I'm going to divert it, and I'm going to send it to my own code. So I'm going to, instead of go to the normal write code, I'm going to go to my own write code, which I think I called rkit underwrite, maybe? rkit underwrite. Now, if I just completely take over and take care of every write call myself and then return, I'm going to blow up my machine because this write has to work correctly most of the time for anything to work. So what instead I'll do is I'll just put myself in line. My code is going to say, if some special thing happens, then I'll do something that I want to. And in every other case, I'm going to call the official one that I hijacked. So the machine will mostly work as normal, but I just insinuate myself into the flow by saying, well, I'm just going to take over in some special case. So otherwise, call the normal write function. And I'll do the same thing here. I'll take over set REUID. In certain special cases, I'll react a certain way, but in most cases, I'll just react the normal way by calling the official. But do you get it? I'm just saying, most of the time, this is just a waypoint, and I'm just going to call the normal write, and nothing different will happen from ordinary functions. Okay, so what have I decided to do here? So I'm inserting this into in the following way, and I'm saying, and this is weird because I have to copy into a local buffer from the user buffer. And I've decided if this weird word is found in the buffer, then don't do anything. Don't actually execute the write. Otherwise, here's the call the original write with the normal parameters. Do the normal thing. Okay? So I'm just doing this as a demonstration that I can suppress anytime somebody calls write, whether it's a printf, a network operation, a disk operation. If this string exists, ignore the write call. You follow me? So I'm just showing you I can kill this. Now, why would I want to kill certain writes? Maybe if somebody's poking around looking for my rootkit, I want to not allow them to see it. So this is a way of suppressing output in certain cases. All right, so let's go and actually install this thing. And the install looks like this. So obviously I need sudo, duh, can't modify the kernel as a normal user. And insmod means insert module or install module. And if I do lsmod, I can see all the kernel modules currently, and my rootkit is not hiding itself. I could make it hide itself, and the original suckit rootkit does hide itself such that when you do lsmod, you don't see it. It's not that hard to do. There's a system call that lists the kernel modules. You just hijack it and then suppress yourself. Okay, so it's installed. So if I say echo hidden like this, it shows. But like this, it doesn't, because my rootkit is noticing that this is being output and decides to kill the write. If I cat out the source code, Here's my I'm surprised that line is there. Sometimes when it's outputting, it'll output part of this word as a separate write, and that won't be caught, right? So if you output the first 3 characters and then you output a second, those are 2 separate system calls. My code won't catch it because it won't appear all at once. All right, so that's kind of interesting, not really, but kind of. I can suppress writing the word H1DD3N. But also in my rootkit, I hijacked another call. I hijacked set RUID. And here's the hijack. It says, if somebody calls set RUID, regardless of who they are, they can be anybody on the machine. If they call with parameters real is 1337 and effective is 1337. No, if not this, right? If somebody calls with other than 1337, 1337, then just call the original. Do the normal system call and go away. But if they are both this, then I'm going to set their user ID to root. I'm going to give them a 0. And this special stuff, it used to be simpler than this. I had to change it because the new Linux, not new anymore, but 3.4 kernel has what's called namespaces, so I had to do some extra work. But trust me, this code just sets you to root. Okay, so what's the exploit? What's this doing?
It allows you, whenever you want, to set your user ID as root.
And what do you do to get root? Since this is currently installed, right? I've got this kernel module installed. So what should I do if I'm just a regular guy on this machine? In fact, could you guys do this right now? You could. All of you are on Razor, yes? I just have this module installed. What could you do right now?
Could set real and effective user ID as.
You could write a C program. You could call set RUID if you type really fast right now. You could call it with parameters 1337, 1337.
This is the real easy solution to 12.
This is the solution to all 15
All
levels.
15 of them.
Right? All you have to do is write this. Call this function with 1337, 1337, and then spawn a shell. In fact, I did that, right? I'm not using sudo here. All I'm doing is calling. Without that kernel module, this wouldn't work. Okay, it's gone. Everyone calm down. So now what happens when I run test? I just get a spawn shell and I'm just nobody still, right? I'm just JR Black. It doesn't work anymore because the kernel module is not installed. But with the kernel module, I got a pound sign, right? And I really am root. It's not just a fake pound sign or something. I'm really a super user. So that's a useful module, right? I mean, who's going to think to accidentally call set RUID? Just in case you guys type fast. Get this out here. Who's going to ever think to call set RUID with 1337, 1337 just on the off chance that it lets you be root? No. I mean, that's supposed to be sort of an obscure backdoor. So that's a way to allow persistent access, if that's always there. Anytime you're on the machine as a normal user, you can become root pretty surreptitiously. Now, you need to hide yourself on the disk. You need to hide yourself on the process table. You need to hide the kernel module. All that stuff has to be hidden. And hiding everything perfectly is really hard. But the best malware ever written has never been seen by anybody, right? People will go, oh, it's Stuxnet or Flame or something. Like, no, the best malware is malware we don't know about because it's perfect. You know, it's never been discovered or seen. All right, so that's a whole separate class on how to write rootkits and be stealthy and all that. But that wasn't part of Razor, obviously. Okay, so there's still some shellcode in one level on the next, so we're doing 10 more levels coming up on a new machine. And I know you're still not all, most of you are focused on Razor, and that's good. But the next 10 levels, we'll do 5 and 5. Most of the time you're going to be exploiting from a browser now, not from a shell prompt. There is one level that still has some shellcode, so don't forget about machine language altogether. But most of them don't have anything to do with binary exploits. Mostly it's going to be web-based. We didn't talk about Windows. Some people care, some people don't. Windows is still very relevant and will be for your entire lifetime probably, because offices still use Windows. Academics, less and less. We've been going to Macs mostly for some reason. And maybe that'll overall happen. And of course, the mobile segment is huge now. And so we've got Android, which is Java and Linux. And iOS is basically a mini version of OS X or Mac OS, which is a FreeBSD offshoot, so which is like Unix again. But Windows will never go away. When you start working on the next 10 levels, some people find it way easier because you're not in GDB pulling your hair out with pointer math. Some people find it way harder because they haven't done much with the web. And at least with GDB, the only thing you care about is assembly or machine language instructions and pointers. And you understand what your world is. It's very constrained. And you know you've got to get that number written to that address and you're going to win. But once you open up this box of the World Wide Web, you've got JavaScript and CSS and HTML on one end. You've got PHP and SQL on the other end. You've got this massive set of standards called like the HTML, HTTP standard, the JavaScript, ECMAScript standard. It's these vast languages, and you're staring at this going like, I don't even know where to start. Right? With Razor, you had this much code, and you knew there was a vulnerability somewhere. You had to figure out what it is. Is it an integer overflow, a buffer overflow, a format string problem, off by one error? In the browser, you're just like, I get this giant web page, there's some server on the back end, and I've got to figure out where there's a vulnerability. I don't even know where to start looking. So that can be overwhelming. But remember, Nick and I are here to help. So don't beat yourself up for 10 hours. Spend a couple of hours. If you can't figure it out, ask for some help. And if you're not that good in PHP and JavaScript, you'll get better. Time. And you'll get better at using, who uses Chrome in this class? About half of you, maybe a little over half. Who uses Firefox? And what about Safari? Okay. So I only use Chrome these days. I used to be a big Firefox user. So I use the Chrome console quite a bit. And getting good at that's very useful for this web-based stuff. There are analogous tools in other platforms as well. So I won't be able to help you as much there. But also, there's another tool that we're going to be using heavily called Burp. Who's ever used Burp? Just Anya. Burp is a proxy. So Burp is a program, it's written in Java. It runs on your local machine, and you set your browser to Burp as a proxy. So you're saying, I would like to be man in the middle by my friend Burp. And it's going to watch all the traffic on the way out of your browser to the server and all of the traffic from the server back. And it will let you do things like capture a request, and you can hand modify the headers. You know, and if the server is like trusting what's coming out of the browser, because you know, hey, I served the JavaScript and it ran, it must be sending me something back that's trustworthy. No, you take Burp and whatever was generated, you can by hand perturb it, change it, modify it. You can set cookies. Delete cookies. You can add get parameters or post parameters. And so that I can talk about, and everybody will probably, I assume, use the same Burp proxy because that's the tool that comes with Kali, and it's the tool that's most widely used. So yeah, that's handy. Yeah, anyway. All right, so I'll stop here. And on Tuesday, we'll pick up and we'll start talking about web-based stuff, which is kind of dry, especially if you already know HTML and CSS and JavaScript. It'll be less exciting, but anyway. All right, so have a good weekend, and I'll see you Tuesday.